Swayam Prabha. Digital India. Educated India.
So, now we will look at condensation. So, as I said, condensation happens when locally the surface temperature is below the saturation temperature of the vapor, assuming that this is a pure vapor environment. So, that means there is only single component, which is water vapor, right. There is no air. If there is air, then it does not have to be less than saturation temperature, but what is the temperature required for condensation if there is an air mixture? Just it should be below the dew point temperature, that is it. So, dew point temperature may be slightly below your ambient temperature, right. Whereas, if you are using single component, if it is case of water, then if this surface temperature is say 90 degrees or 80 degrees and you have only water vapor. So, this can happen if you completely evacuate the system and do a very controlled experiment, where you fill only water vapor and then the surface temperature can be maintained at 90-95 degrees, you will start seeing condensation happening even at that temperature, right. So, now there are two types of condensation, just like boiling, we saw nucleate boiling and film boiling. Condensation also has film condensation and a nucleate condensation. This is also called as the drop wise condensation. So, very similar mechanism, but exactly the temperatures are exactly maintained the opposite way. And in the film wise condensation, what happens is you have the vapor outside and you have gravity acting down, okay. You place the plate vertically, maintaining at a lower temperature than the saturation temperature, and you see the vapor has to get condensed locally when it is in contact with the plate, because again coming from the thermodynamic diagram. So, when you plot, for example, temperature versus specific volume or entropy, you have this vapor dome, and at each pressure you have these states. So, this is a different increasing pressure. So, therefore, once the temperature, for example, in this case this is at 100 degrees, 1 atmosphere. If your surface temperature is 80 degrees, so obviously the state of water has to be liquid. So, therefore, it will now condense, and then when it condenses, now the condensate now will get accumulated. As you go down, there will be more and more condensate mass, because there is some condensate at the top, and as you go down, this condensate is going to grow in volume, in mass, and therefore, this will form like a boundary layer, okay, some kind of a film which is covering the entire plate, and it is going to flow down. So, this is called a liquid film condensation, okay. It is like a falling film. So, you have to keep the plate vertical, otherwise the condensate will not flow. So, if you keep it horizontal, it will condense and it will blanket the entire surface, but it will not move. So, you need to therefore keep it vertical with gravity aiding the flow of the condensate. Now, the other type of condensation is basically nucleate condensation, where the droplets are basically nucleating, just like bubbles nucleate. In boiling, the droplets can nucleate and then they grow in size, okay, as the condensation progresses, and depending on the type of surface, these droplets can coalesce with the smaller drops, they can become a larger drop, and finally once it reaches a critical size. So, if you keep the surface tilted or keep it vertical, due to gravity they have to roll down.
Say actually when we don't have any control over the polishness of the fineness of the surface, how does it differ, like how does it yield two different condensations, like film condensation?
Yeah, so I think that is a good question. So, if you just keep for example copper vertically, you do not expect dropwise condensation to happen by default. You will generally see film condensation because it is a by default it is a super hydrophilic nature. So, if you put water, it will be around 70-80 degree contact angle. So, you will end up seeing this kind of film condensation. So, in order to control this and to reach this dropwise condensation, you have to change the wettability of the surface. So, you have to do some treatment to the copper so that it becomes hydrophobic or super hydrophobic, so that the contact angle goes above 100 degrees, and then you will start seeing that the film dropwise condensation automatically happens. Okay, because the dropwise condensation requires the wettability of the surface to be changed, it does not happen by itself. Or if you take a surface which is by default giving a very high contact angle with water, then that will automatically create dropwise condensation. But the advantage of dropwise condensation is, as you can see, this film condensation is forming resistance between the vapor and the surface, because what is happening in condensation, it has to basically give away heat. In boiling or evaporation, it has to take heat from the surface to boil, but here it has to basically give away heat to the surface. So, the heat has to penetrate through this vapor layer, which is again a low thermal conductivity layer, which is not very efficient. So, therefore, if you maintain dropwise condensation, so this problem is not there. So, the condensation heat transfer is much better when you have dropwise mode of condensation than film. So, therefore, you will see generally heat transfer rates are more than 10 times larger in dropwise condensation.
If that is the case, why do industries prefer film condensation?
It is not like they prefer, it is not like they prefer, it is not, in fact it is the other way. They like to improve the condensation heat transfer by coating these surfaces and making them more super hydrophobic, so that actually dropwise condensation happens. But if you do not do all those coatings by default, yes, film wise condensation is there. Yeah.
So, right now this is the normal practice, but they
by default, if you look at most of the metals, in fact with water, the default contact angle will always be less than 90 degrees. So, most likely you will end up with film condensation. And one more point is that it is not always that as coating a surface super hydrophobic will guarantee a high heat transfer coefficient, because if you, this is only with pure vapor. If you have a vapor plus air, what happens is the air molecules will act like a layer of resistance through which these vapor molecules have to diffuse. So, in that case, when you have a super hydrophobic surface, the nucleation itself will not happen, because the nucleation has to happen only by diffusion of these vapor molecules through the layer of air which is acting like a resistance. And if see that is basically a fine balance. So, if you have a normal hydrophilic or a super hydrophilic surface, the nucleation will be much better, but then very soon it will become film condensation. So, if you have a hydrophobic or a super hydrophobic surface, the nucleation will be delayed, but it will be maintaining mostly in the dropwise condensation. So, if you do this in the presence of air, now even the nucleation will be delayed to such an extent that you do not get any condensation happening and the condenser will not work. So, maybe it is better that you operate in a film condensation mode in that case. So, therefore, it is not as simple and straightforward as such. But generally, if you compare, the rates of condensation with dropwise condensation is definitely much higher than film wise condensation.
Except this hydrophobic layer, surface roughness does not play any role.
Roughness also plays a role. See, just like nucleation in boiling, the nucleation in condensation is also a stochastic process. So, you do not see all the time with a uniformly rough surface nucleation happening exactly the same way. When you keep taking these experiment images, maybe some 1000 images over a period of time, you will see that the nucleation density and frequencies are completely different. So, that is also completely stochastic process. So, the theory of film condensation was first actually solved analytically by a person called Nusselt, after whom the Nusselt number in force convection came into picture. So, he considered a kind of profile like this. So, you have a vapor outside and you have a condensate which is falling as a film, and you see the condensate is flowing like this, like a boundary layer, and when he took the velocity profile looks something like this. Okay, so, this is a no slip boundary condition here, and then velocity profile gradually increases, it reaches maximum value somewhere close to the thickness of the film, not exactly at the edge of the film, but somewhere close to that, and again it decreases and then it reaches 0, because outside the film is not completely stationary, outside the vapor is not completely stationary, the vapor is also flowing due to gravity, right. So, there is a very small velocity there, but quickly after some distance the vapor velocity will be going to nearly 0 value, and at the interface it has to satisfy the continuity of velocities. So, liquid velocity should be equal to the vapor velocity, or let me use V, and similarly the shear stress due to the liquid should be equal to the shear stress due to the vapor. So, tau L is equal to tau vapor, which means that my mu L du by dy, my y is in the direction normal to the plate at let us say y equal to delta, should be equal to mu V du by dy at y equal to delta, and this is for the liquid, this is for the vapor. Okay. So, it has to basically satisfy the continuity of velocity and stress. Now, when you enforce the stress continuity, the viscosity of the vapor is much smaller than the viscosity of the liquid. So, what it means, in order for this to be equal, this gradient of velocity has to be very large in the vapor. So, that is why you see that it goes from this maximum value to 0 in a very rapid manner. Okay. So, what Nusselt did was, in order to make it less complex, he assumed that this entire term was 0, because the viscosity of vapor is so small, it is maybe 5 orders of magnitude smaller than the viscosity of liquid. He completely took that to be 0, so that in that case your du by dy is 0 at the interface, which means that he assumed that the peak will happen right at the edge of the film. So, this was basically his velocity profile, and temperature profile actually looks more non-linear like this, but he assumed a linear profile which is between your T saturation temperature at the interface of the film, and then at the surface he took this to be the wall temperature. Okay. So, basically a much simpler approximation to the more complex non-linear convective temperature profile he has assumed, and also the velocity profile he has simplified such a way that the maximum velocity happens right at the edge of the film. So, with that so he had so this is how it looks. So, this is the Nusselt's approximation, this is not the actual case, but this is the Nusselt approximation, and the same thing with temperature profile. So, the idea here is making sure that the shear stress is basically negligible, because the viscosity of the vapor is much smaller than the liquid, that practically you do not have to consider the shear stress, and momentum changes in the film are negligible. Now, therefore, within the film any momentum change across the film, for example along the length of the plate, will be very small and can be ignored, and apart from that the condensate of the flow in the film is laminar. So, if it is turbulent or something like that, then this theory will not be very accurate. He also approximated the temperature profile to be linear instead of non-linear profile. So, with that so I am just skipping the derivation, but you can actually go through it in the lecture when I post it. So, he assumed a very small control volume like this, where the condensate which is entering at x is m dot x, and what is leaving is m dot x plus dm dot x. Okay. And the condensate is condensing exactly at the interface of this liquid vapor film. So, this interface is at T sat. So, the condensate is exactly condensing here. So, this is dm dot due to the condensation, right. So, this basically is going to add on to the m dot x to basically increase the mass flow due to the condensation, and this condensate heat has to be removed from the wall. Okay. So, there is also a heat transfer, the condensation heat transfer has to be effectively carried out from the wall. So, this is also something that, so you have to consider mass balance, momentum balance and energy balance for this derivation. And finally, if you do that, so you get the expression for the condensation heat transfer coefficient, which turns out to be inversely proportional to the condensate film thickness. And from the Nusselt theory, whatever I have briefly explained, so he has got the expression for delta, which is the film thickness, which is varying along x, of course, because it is growing. So, he has obtained this expression and therefore, the expression for condensation heat transfer coefficient. Okay. So, from this you can calculate what is the average condensation heat transfer coefficient by integrating this local heat transfer coefficient along the entire plate length, and he gets what is this H. So, therefore, this is the same expression that was later adapted for film boiling. The only thing was they added a coefficient, so that the coefficient was tweaked for film boiling, but essentially the expression comes from the Nusselt condensation theory. Okay. So, now there is one small change that you have to do sometimes, because you have this HFG, which is the latent heat of vaporization or condensation. The assumption in the Nusselt theory when he developed this was the temperature of the liquid film at the interface was exactly at saturation temperature, but you can have a vapor which is possibly even superheated, which is then condensing. Okay. So, in that case how do you account for that? And the other thing is the wall, from the wall to the interface there could be also subcooling. So, he did not consider the subcooling and superheated vapor effect. So, later people just added that. So, and they call this as a modified latent heat of vaporization. So, HFG star, now if you consider that the final state is a subcooled liquid instead of saturated liquid, then you can add a difference of sensible heat due to the subcooling from Tsat to the surface temperature. And similarly, if the vapor that enters the condenser as superheated vapor at temperature Tv instead of saturated vapor, then you have to consider some degree of reduction from the superheated state to the saturated state. So, that is accounted for a sensible reduction in the temperature by this. So, therefore, the final HFG star can include both the effect of subcooling liquid as well as reducing the vapor temperature from a superheated state to the saturated state. So, these effects were later incorporated additionally into the correlation. So, the correlation remains the same, only the HFG is corrected to account for the modified latent heat of vaporization. And the other important thing is that when you look at the film condensation, the condensate is going to flow down, and there are different regimes of condensation in the film wise condensation itself. For example, you use what is called the Reynolds number here. So, the Reynolds number is calculated based on the hydraulic diameter. If it is, for example, a plate, accordingly you use only the length. If it is a cylinder or something, you use the equivalent hydraulic diameter, and then you have the mass flux, which is rho times the velocity of the liquid film divided by the viscosity. Okay. Now, of course, the hydraulic diameter is 4 times cross sectional area by perimeter, and you can write it in terms of the mass flow rate. So, if you know the mass flow rate, you can actually use it to calculate what is the Reynolds number locally, and you can classify the regimes of film wise condensation. For example, if you have Reynolds number less than 30, so this is called as a laminar wave free condensation. So, this is looking like this is your classical film condensation for which Nusselt developed this film condensation theory. But if you increase the Reynolds number after 30 up to about 1800, you find the small wavy patterns which are established because of some instabilities, and this becomes a wavy but still laminar regime. And now if you go to very large Reynolds numbers above 1800, you see that there is also turbulence in the fluid, that is in the liquid film you see lot of turbulent effects, and it becomes a completely turbulent film. So, generally the laminar the Nusselt theory is valid only for the wave free laminar condensation regime, but people later developed some empirical correlations when they move to even turbulent film condensation. But usually very rarely you want to go to that kind of lengths, where turbulent condensation comes into play. And what happens if you change the geometry of these condenser tubes instead of just a flat plate, for which the condensation theory was developed by Nusselt? What happens when you change this geometry to horizontal cylindrical tubes or sphere? So then what they used was they had the same correlation, whatever that you have using here, and instead of using 0.943 for the average Nusselt heat transfer coefficient, they use 0.729. So if it is a cylindrical tube, so they just change the coefficient accordingly. So apart from that, the other parameters were exactly identical to what was developed by Nusselt for a flat plate. So essentially there is no hard analytical expression when you change the geometry. So it is primarily developed for a laminar wavy free regime for a vertical flat plate by Nusselt, and later on it was slightly tweaked or adapted to other heater configurations depending on whether it is a cylinder or a sphere. Okay. So I am just going to skip some of this because we do not have too much of time, but of course when you are talking about a situation like this, when you have tube bundles, so you have horizontal tubes one below the other, what happens is there is a condensate. So you have vapor which is flowing, and inside the tube you have a cold water. Okay, this is going to condense, the vapor has to condense, and then this condensate will be falling like a film around the cylinder. And it is not just that, it is also going to accumulate and fall on the tube below that. And as you go down, the thickness of this film will progressively increase because it is accumulating from the previous tubes. Therefore, if you look at the heat transfer coefficient for this entire tube bundle, it will be definitely lower than the heat transfer coefficient of a single tube. The reason being that the thickness of this condensate is progressively increasing along the downward direction. So therefore, to account for this correction, people use a factor of n instead of just the diameter of a single tube, they use n times d, and as you increase the number of tubes, the heat transfer coefficient of this combined n tube bundle will be corrected. So it will be reduced accordingly, right, compared to a heat transfer coefficient of a single tube. So this is the standard expression that people use in industry to estimate or design the tube bundles for condenser.
So this is for both film and drop or only?
This is only film. See, whatever I am talking now is the theory is all assuming that it is film condensation. Yeah. So for drop wise condensation there is no theory. So in that case, as I said, so this is a highly stochastic process because there is a nucleation of drops, and then these drops can coalesce and form larger drops, and depending on the orientation of the surface, these drops can actually be eliminated by gravity. But of course in terms of heat transfer rates, these are more efficient. You have heat transfer coefficients which are 10 times larger than film condensation. But as I said, there are no theoretical models or expressions for drop wise condensation. Most of it is empirical, and any of textbooks should give you a standard empirical correlation for this. So finally, when we conclude condensation, just want to say that whatever we have talked about with Nusselt theory and so on is assuming a pure single component vapor environment. If you have a vapor plus a non-condensable gas, typically air, so how is it going to condense? So in that case, as I said, so there will be a resistance to the movement of these vapor molecules to the surface, and generally the condensation performance in the presence of any non-condensable gas will be poorer, will be much lower than when you have a pure single component vapor condensation. So this is generally the thumb rule. So if you are designing your condenser heat exchanger for only pure vapor, you can expect that when you have a non-condensable gas like air mixed with the vapor, you will see generally much lower values of heat transfer coefficient. Okay, because obviously this is going to cause a resistance to the movement of these vapor molecules. Okay, so with that I think we have quickly summarized condensation. and I want to go into flow boiling now. Before we also look into a couple of tutorial problems. So, what is the time? Okay. So, we can start flow boiling and then give a break. Okay. Now, I think now you have understood the mechanisms of boiling in the sense how nucleation boiling happens. Now, we will extend it to a case where there is a movement of fluid in tubes. So, this is the situation what we are now going to look at, which is called the two-phase flow boiling. And I think Professor Marco has already discussed some of the different aspects of multi-phase flows that you come across, or two-phase flows that you come across when there is a convection, right. For example, people talk about these micro reactors where there is one droplet which is one component suspended in another droplet, and these droplets are used to transport these smaller droplets inside capillary tubes. So, these can be used in reaction like in micro reactors and so on. And similarly, there are many other processes where for example, in microfluidic devices, micro propulsion devices, compact heat exchangers, where you can come across movement of two-phase flows. So, it is not just a phase change happening in a stationary surface, but there is also movement of all these flows that are happening. So, the thing is okay, how should I? So, regarding the reason why do we need to go to smaller sized channels, when we talk about flow boiling, of course, you can do flow boiling in conventionally large sizes, it can be of the order of few centimeters or a few tens of millimeters or maybe 1 millimeter also. But there is also an increasing demand of studying flow boiling in very small sized tubes and channels. So, what is the need for that? As you know, if I have my Nusselt number in a fully developed flow laminar, let us say, so it is a constant value, right. If it is constant heat flux, so this value is 4.36, and in the constant wall temperature case this is 3.66. So, that means my H into D by K is basically a constant, and which means my H is inversely proportional to the diameter. If I therefore have a tube where I plot H on the y axis and the diameter, so as I reduce my diameter, my H is going to go up linearly, right. So, this is the advantage of using smaller size tubes. So, if I want to improve my convective heat transfer rates, my Q is H A into say T wall minus T reference. So, if my heat transfer coefficient is very large, my heat removal rates also will be consequently very large. So, the idea going to very small sized tubes is exactly this. You have a fine control of increasing your heat transfer coefficient even in single phase. So, you do not have to be essentially in flow boiling. Even in single phase, if I change my diameter from 1 centimeter, which is basically you are talking about 10 millimeters, and then you are going to let us say 1 millimeter, I have a 10 times increase proportionally in the heat transfer coefficient. And even if I go to micro channels, if I go to say 100 microns channel, so even I am reducing it from 1 millimeter to 100 microns, I can therefore go to very large values of heat transfer coefficient without doing anything, right. But of course, my pressure drop is also going to go up, because my friction factor is also say let us say function of Reynolds number, and for the same Reynolds number I have a fixed value of F, and then the pressure drop is again going to be very large if I have very small size. So, both pressure drop will increase if I have very small size channels and the heat transfer coefficient. The question is how much therefore you can stop, So, you do not want to operate with channels which are 100 microns, because it is not just resulting in high heat transfer coefficient, but the pressure drop is also tremendously high. So, you do not want to therefore do this at the cost of increasing pumping power. So, one of the reasons is definitely your heat transfer coefficients are very large if you have smaller size channels, and on top of which if you go to phase change, like flow boiling, this will even augment even further. So, if you do the same flow boiling in a let us say 10 millimeter size tube, I get a heat transfer coefficient of say 10,000 watt per meter square Kelvin. Now, if I do this in 1/10 of this, then I get maybe 100,000 watt per meter square Kelvin. So, the same flow boiling also can be progressively enhanced if I do this in a small size channel. So, therefore, working with flow boiling in mini or micro channels has become very attractive, especially if you are targeting cooling applications like electronic cooling, where the size of these electronic cooling CPUs, so these are of the order of 35 by 35 mm square. And if I want to cool this, naturally I want to reduce the size of these channels. Instead of having maybe 1 millimeter channel, I can use 200 micron diameter channels, multiple of them in a parallel arrangement, and I can connect all of them together. I can supply the fluid like this, it goes through all the channels and then comes out. So, if I have many micro channels, each which are smaller in size, more in number, I am going to enhance my heat transfer coefficient significantly, and thereby I get very high heat transfer rates. Now, on top of that, if I do flow boiling inside these micro channels, I also increase the heat transfer coefficient at least by another order or 2 orders of magnitude. So, that is the idea why flow boiling in small size channels are quite important. So, the other thing is from the fundamental physics point of view, when you do two phase flows, for example, today Professor Marco was talking about the flow regimes, right. So, these flow regimes he was showing in these different tubes. Now, these flow regimes can be obtained in two ways. So, one, you have a T junction, so somewhere so I am just going to pass liquid like this in one of this, and then I have vapor or gas or air in another, and then I have a T junction where these two mix and then it flows. Okay. Now, I have the liberty of controlling what is the relative mass flow rate of air with respect to the mass flow rate of liquid. Accordingly, I can produce different types of two phase flow patterns in these tubes. So, that is one way, that is basically an isothermal two phase flow patterns that you can observe when there is no heat transfer, but just you change the relative mass fraction of the air and the liquid that you mix in a T junction, and then you observe how the different flow patterns look. That is one type. The other type is I take a tube like this, I pass only liquid and I heat the tube such that my heat fluxes are large enough that locally my surface temperature is above the saturation temperature, and therefore I can produce bubbles which are vapor bubbles, these are not air bubbles by the way. So, and I can also produce different flow patterns. So, therefore, there are two different types of flow patterns. One is called the adiabatic two phase flow pattern. So, these flow patterns are produced by mixing say air and water, okay, in a T junction, and looking at the different mass flow rates of air as a function of for a fixed mass flow rate of the liquid, and by changing the ratio of the air flow rate to the liquid flow rate, I can look at different flow patterns that are emerging. The other is basically the diabatic, which means I have a non-isothermal or a heated two phase flow. And how do I get this? This is obtained by heating the tube, so that you raise the temperature above the saturation temperature, and then you look at how these vapor bubbles are produced and these are moving. So, now if you look at the difference, this is important between a macro and a micro channel. So, let us say this channel is 3 millimeters in diameter, okay, and whether you are doing either with the adiabatic or with the diabatic, now let us say that we are heating the tube. Okay. Now, with the 3 mm diameter macro channel, you start with pure liquid initially, okay, and then once the surface temperature of the tube at some point will be above the saturation temperature, there is a onset of nucleate boiling, and then these bubbles, these vapor bubbles start emerging. Okay. Now, usually these on a large diameter tube, these vapor bubbles will start emerging from the lower half of the lower part of the tube, because of the buoyancy they can detach and they can rise up, and these will be progressively going downstream, and there is also a flow of the liquid here. It is not a quiet fluid, right, there is a fluid with a given convective velocity, and therefore these bubbles are advecting downstream, and then as you continuously supply heat, now you are basically supplying heat with a uniform heat flux. So the surface temperature is increasing along the length of the tube. So as the surface temperature is progressively increasing above saturation, you see that the bubbles sizes are becoming larger because you are adding more heat to the bubble. So more fluid is getting converted into vapor, and then these pockets of vapor is enlarging in size, and as you go downstream it comes to a point where the bubble cannot grow anymore because they occupy the entire diameter of the tube. So this is initially called the bubbly flow, and then you reach a point which is called the slug flow. So here the slug means the vapor has gone to the size almost of the diameter of the bubble, and there is only a very thin liquid film which is separating the wall from the vapor bubble. The core of the bubble is basically vapor. Okay. So this is called as a slug flow, and from there if you continue supplying heat, what happens is even the liquid film, which is a thin film, is going to evaporate, and it will become what is called as an annular slug flow, where the entire liquid film is pushed to a very thin annular region, and the center core is completely vapor pocket, and further supply of heat will result in a complete evaporation of the film, and it will lead to what is called as a dry out. Okay. So now if you plot the quality of vapor, that is the vapor mass fraction. So I am just going to plot this vapor mass fraction x, which is the mass flow rate of the vapor by the total mass flow rate of the flow. So right at the inlet this is going to be 0 because it is pure liquid, right. So 1 will be pure dry out because its vapor fraction is 1. So it starts from pure liquid, and then progressively it will go increase, and then at the point of dry out it will reach the value of 1. Okay. Now if I do the same experiment on a micro channel which is of the size of 100 microns or something like that, you will not see these bubbles are growing from the bottom and rising up, because the size of the channel is so small that once the bubble nucleates and immediately it reaches the size of the channel, so it cannot grow like a bubbly flow in a macro channel. So the bubble nucleation will happen very quickly, it will proceed to a slug flow and to an annular flow. So you do not have all these instances where you have coalesced bubbles and then all these bubbles are rising, and then coalescing and reaching, because now the bubble itself which is nucleating is big enough to occupy the entire diameter of the tube, and immediately after the bubble nucleation there is a slug flow and then an annular flow. So you do not have all these intermediate regions generally seen in the case of a micro channel. So and then very quickly from this it goes to a dry out at the exit. So in that sense the number of regimes that you come across in a micro channel are few compared to what you see in a macro channel, and the reason behind that is the surface forces are going to be more dominant in a micro channel, and gravity forces are negligible in comparison.
In such a case, how do we actually control the dry out, because it's very sensitive?
Controlling dry out,
I mean, eliminating dry out.
it depends on the length of the tube. So therefore if you have a very long tube, inevitably you have to reach a dry out. So even if you have a micro channel with a reasonably small length, you may sometimes go very quickly into the annular flow regime very fast, and if it is a slightly longer tube, the dry out will happen quickly in that case. But increasing the flow rate will actually change this dry out, because that's where the control in convective boiling comes. So if you do not operate the liquid flow rate, it is going to dry out faster in a micro channel, but if you increase the flow rate, definitely the quality will now come down. The quality will in this case, of course, because coming down means it will become more towards the liquid side.
Maybe choose a liquid also.
Yeah, so if you increase the mass flux, definitely at a local position, at a length, the vapor quality will be basically lower when you keep increasing the flow rate because of the convective effect. because whatever energy that you add is not going completely into the entire volume, but it is just advected, right. So this is a very complex interaction when you look at flow boiling. Okay. So there are a few non-dimensional numbers, we will quickly go over them and then take a break. So one is called the Martinelli parameter, which is basically the ratio of frictional pressure drop when you have only a pure liquid inside the tube to the case of only when you have a pure vapor. Okay. So imagine that this tube, now you have a mixture of two phases, right, liquid and vapor. If you have only pure liquid, so what will be the pressure drop versus what will be the pressure drop if you have pure vapor, and then take the ratio. This is defined as the Martinelli parameter. The reason why we use this is the most common parameter by which the two phase flow pressure drop is calculated. When you have two phases in a tube, so the two phase pressure drop is calculated as a function of this Martinelli parameter. Apart from that, we have another important number called the convection number. So here we use another small x, which is the vapor quality, not to be confused with the Martinelli parameter. Okay. So vapor quality is what is the mass flow rate of vapor at a given cross section divided by the total flow rate. So therefore this x square is different from this. Okay. So then we also use other non-dimensional numbers when we build correlations for two phase flows, which are called as boiling numbers, for example. So boiling number is given by the ratio of the heat flux divided by what is the product of mass flux G and the latent heat of vaporization. So for a given amount of heat that you are supplying to the tube, how much of this is going into the phase change process is given by this boiling number. These are a couple of numbers which are not very significant, but sometimes may be useful to understand also the regimes. But the more important numbers, I am sorry, I think this is 6, 7 and 8, are the bond numbers. The bond number is basically the ratio of the buoyancy force to surface tension force, which is important in two phase flows, especially when you are studying two phase flows in small channels. Somebody wants to know whether the buoyancy is important here or is the surface tension important. So you do that by calculating the bond number. So typically if the bond number is less than say 2 or 3, so it is dominated by surface tension as opposed to buoyancy force. So in all the smaller size channels like micro channels which have diameter of 200 microns, the bond numbers are sufficiently small enough that you can ignore the gravity effects and then say only surface tension is going to drive the phenomena that is happening. So it is mostly capillary driven phenomena. People sometimes use another number which is very similar to bond number. So they call this as Eötvös number. I think some papers you will see Eötvös number, but essentially it is the same as bond number. So there is hardly any difference. And then the other important non-dimensional number is called the capillary number, which is the ratio of viscous force to the surface tension force. So generally when we talk about two phase flows, so you have inertia force, you have viscous forces, you have surface tension forces and you have gravity forces. Okay. Now these are the four important forces. So all your non-dimensional numbers are combination of two of these forces. So when we talk about bond number, it is buoyancy by surface tension. When we talk about capillary, it is viscous by surface tension. Reynolds number is of course inertia by viscous force, and then we talk about Weber number, which is basically inertia by surface tension, right. So therefore with these four forces you can define 3 or 4 non-dimensional numbers to basically include the ratio of these two forces. So Weber number again is an important number where we use inertia by surface tension. So sometimes when you talk about drop impact in sprays, so we use characterize the strength of this impact velocity using the Weber numbers. Sometimes we also use this to characterize what is the inertia to surface tension force in flow boiling as well, but mostly Reynolds number itself is sufficient for that. So bond number is also important, capillary number is also important, and then people use other numbers like Ohnesorge number. So Ohnesorge number is again it is a combination of the ratio of viscous force to in the denominator both the inertia and surface tension forces. Sometimes they are used in atomization studies We do not use Ohnesorge number in flow boiling in tubes and all that. So, primarily in sprays you come across Ohnesorge number. There are different spray regime characterization maps based on Ohnesorge number. In fact, so Ohnesorge is a German name. So, Ohne means without, Sorge means worry in German. So, it is the name of a person. So, Ohnesorge means without worry. So, it is a surname, but people have used it like that. Okay. So, and then again when it comes to heating, flow boiling, we use what is called as a Jacob number. So, this is very important. So, for example, when you do flow boiling, just like in pool boiling, you can have a subcooled pool boiling versus saturated pool boiling. Similarly, you can have a subcooled flow boiling versus saturated flow boiling. So, in order to distinguish these regimes of flow boiling, whether you subcool it or saturate before you send the fluid, so you use the Jacob number, because the Jacob number is the ratio of what is the sensible enthalpy that is added to the liquid divided by the latent heat of vaporization. And obviously, the Jacob number will be what if you have a saturated liquid? If you have saturated liquid boiling, flow boiling, then what will be the Jacob number? Hmm? 0. So, because your delta T is 0, because you are already reaching a saturation temperature. So, anything apart from 0 means it is basically a subcooled liquid, right. Okay. So, we will stop here, we will take a brief break. Again we will come back to the different flow regimes little bit in detail, and then we look at correlations for calculating pressure drop and heat transfer coefficient during flow boiling in small size tubes.